Okay, so last time I introduced the following definition. Say X is connected, disconnected, if we can write X as a union of U and V, where U and V are non-empty disjoint open sets. And otherwise, we say X is connected. So if it's impossible to write X as a union of two non-empty disjoint open sets. Another way we can say this is, well, whenever we can write X as U union V, with U and V non-empty, then either U contains a limit point of V, or conversely. Okay, so this is equivalent definition of what it means to be connected. And to see why this is equivalent, you just have to think about the subset trichotomy. If a set is not open, then I guess its complement is not closed, and so the set contains a limit point of its complement. Okay, fine. So let's see some examples. So first, let's take this subset of the real line. So we expect that this set is not connected, or that it's disconnected. And indeed, that is the case. Because, and so let me not write down this carefully, but okay, here's U and V, open sets, non-empty, and they're disjoint. And their union, or rather, I guess U should be the intersection of this interval with, well, no, this isn't exactly the right way to say it. Sorry. It's potentially going to be confusing. Let's take X this, and we say U is 0, 1, and V is 2, 3. So I guess the only thing I should say is why these are open. So, and this is the subspace topology on this subset. So open sets, an open subset of X is a set that's the intersection of an open set of R with X. And so 0, 1 is open because, well, you can take a slightly larger interval that intersects X just in the closed interval 0, 1. And similarly, 2, 3 is also open. Okay. Yes. I guess it would have been potentially easier on me if I had started with an interval, open intervals, but both of these examples are disconnected. Okay, so disconnected. Okay, another example. Let's take X to be Q. This is also disconnected. Since we can write X as, well, here's one way to do it. Two open intervals whose union is X and they're disjoint. So here we're using that square root of 2 is irrational to make this work. A couple of other examples. So R with the discrete topology is disconnected. So is disconnected. Which, well, okay, so I mean, everything is open. So you just have way too many open sets to work with. And so it's easy to find disjoint open sets whose union is everything. On the other hand, R with the indiscrete topology this is connected. Well, there simply are just not enough open sets. I mean, you can't find, so here the only open sets are R and the empty set. So in this topology, there doesn't even exist disjoint non-empty open sets. The only non-empty open set is R. There's not two disjoint. Okay. All right, so right, the first thing we would like to prove is that R with the standard metric is connected. Standard topology, rather, sorry. Right, so a remark about this. So connectedness is a topological property. Topological property. Just to say if X and Y are topologically equivalent, then X is connected if and only if Y is connected. So by the prop, open intervals like 0, 1 are also connected. Since 0, 1, the open interval is topologically equivalent to R. I'm not sure if we said that or proved it, but at this point, you can do that. Okay. There's one other thing I need to say before we can prove the proposition. So recall from last time, this is the least upper bound property of R. Which says that any non-empty subset A in R that's bounded above has a least upper bound. Right, so this is a special property of R. Maybe I'll remark, this is not true if you replace R with the rational numbers. For example, if you consider A to be this subset of rational numbers, this is a non-empty subset of rational numbers, which is bounded above, but it doesn't have a least upper bound in the rational numbers. The least upper bound of this set is square root of 2, and square root of 2 isn't rational. Okay. So this least upper bound property, as I was saying last time, it's one of the things that makes the real numbers special. And we're going to use it in the proof of this proposition. Okay, so let's now prove the proposition. Let's just do it here. So you'll see how the least upper bound property comes up here. All right, so proof. So suppose for a contradiction, that R is disconnected. So we can write R as U union V for non-empty disjoint open sets U and V. So U and V are non-empty, so we can take A in U and B in V. So let's consider, let's call it A, the set U intersect the interval AB. So, okay, before we do that, let me just remind you what we're going to try to do. So, well, we want to reach a contradiction, which is, and we're going to do that by showing either U or V is not open. And the way we'll do that is to find a point in U, which is a limit set of V, or a limit point of V, or a point in V, which is a limit point of U. Okay, so if we can do that, then either U or V is not open. Okay, so that's what we're aiming for. And I mean, the intuition is, I mean, if you try to split up R, maybe I should have done this before starting the proof, but you know, the obvious ways to split up R are some picture like this, where you take, you know, everything up to some number T, and then everything greater than or equal to t. And well, of course, in this case, v has a limit point of u, which means that v is not open. Right, because its complement isn't closed. Okay, right. But so in the proof here, we're starting with some decomposition. We don't really know what it looks like. It maybe doesn't look quite like the picture I just drew. But okay, so we find 2 points A and B, and we look at this intersection. So this intersection A, this is non-empty, since the point little a is in here, and it's bounded above. So A has a least upper bound. Let's call it Z. So this is like the, so let me draw a picture. So here we have the interval AB, and U intersects this interval in some way. I mean, U is an open set, so I don't know, it looks maybe like this. Something like this. But there's so the intersection of this interval with, so inside of this interval, there's some least upper bound for the set A. So A is just sorry, I'm saying too much here. So in this picture, the least upper bound is like this point. So now let's consider, there's 2 cases. So case 1 is that, so Z is either in U or in V. And let's just consider these 2 cases separately. Z is in U. Well, this implies, so then Z is a limit point of V, because there's 2 alternatives based on the subset trichotomy. If you have a point in U, either that point is, oh, sorry. Yeah, so let's focus on V. Z is not a point in V, which means either it's an exterior point of V, which means it's an interior point of U, or it's a limit point of V. So sorry, I should write this. So Z is either an exterior point or a limit point of V, because Z is not in V. But if Z was an exterior point of V, then it would be an interior point of U, which means that there would be points of U. So then the picture would be something like this. We have Z, and there, you know, around Z, there's a small ball which is contained in U. But this can't happen because Z is supposed to be an upper bound for U. Z is supposed to be greater than every element of U. So this can't happen because Z is an upper bound. for U. Okay, and case 2 is that Z is in V, and let me just say this is similar, and I would encourage you to think about how to finish the argument in this case. I have a feeling this was potentially confusing. If we were synchronous, I would stop and hopefully have you pester me with questions, but I guess we'll have to do that over at Piazza. Okay, so let's once you show case 2, you reach a, right, so the upshot of case 1 is we conclude that Z is a limit point of U, or of V, sorry, which means V is not closed, so U is not open. And similarly, in the case Z is in V, you show that Z is a limit point of U. Okay, and so in either case, this is showing you can't write R as the union of two open, non-empty disjoint sets. Whenever you have a union like this, one of them is not going to be open. All right. Okay, so that is a useful thing to know. And let me just remark that the same argument shows that the interval 0, 1 is connected. Which is what you would hope. Okay, so let's switch gears a little bit, and I want to talk about the relationship of connectivity and continuity. Okay, so far we have the definition of connectedness and disconnectedness, and we know some basic examples. And now I want to explain how you can use continuity to characterize being connected or disconnected, and how you can use that to show things are connected or not. So let me start with a lemma, which says that X is disconnected if and only if there exists continuous surjection from X to a 2-element set. Let's say -1, 1. Let me say 0 and 1. So here I'm viewing this with the discrete topology. So continuous with respect to the discrete topology here. So let's prove this. The proof is not so bad. So the forward direction, so if X is disconnected, we can write X as U union V. And so then, well, let's define F in the following way. So F of X is, well, it's 0 or 1. It's 0 if X is in U, and it's 1 if X is in V. So let's see these properties. So this is continuous because U and V are open. It's surjective because U and V are non-empty. And it's well-defined because U and V are disjoint. Okay. Conversely, given F, define U to be F inverse of 0 and V F inverse of 1. Sorry, my pen. So, okay, these are non-empty because the map is surjective. They're disjoint because, well, something can't map to both 0 and 1. And their union is everything because the map is, well, their union is everything, just trivially. Okay, so that's the lemma. And here's an example of how you can use this. Let's take GL2R is these 2x2 invertible matrices. So I claim this is disconnected. And, well, okay, and to prove this, I'm going to use the lemma. I'm going to give you a function. So consider a function. Let's take values in 0 and -1 and +1. And the way it's going to be defined is f of some matrix A. Maybe I just write the matrix here, A, B, C, D. It's 1 if AD minus BC is positive, and it's -1 if AD minus BC is negative. So this is continuous. I mean, this is essentially a composition of 2 continuous functions. So first we have the determinant, which is AD minus BC, which takes us into non-zero real numbers. And then we have the sine function, which takes us into plus or minus 1, which just assigns to a real number, is it positive or negative? And this is continuous. And so this composition is F, which is continuous. And it's surjective because, well, okay, it's not hard to find things that map to, so this has determinant 1, this has determinant -1. So, okay, F of this is 1, F of this is -1. Okay. So GL2R is disconnected. It has 2 pieces, essentially based on whether the determinant is positive or negative. So remark that, well, so for SL2R, which is a subgroup of GL2R where the determinant is 1, this argument doesn't work. Because, well, if the determinant is 1, if I just look at the image of SL2R under F, everything maps to 1. The determinant is always positive. So this map won't be surjective when restricted to SL2R. And in fact, SL2R is connected, and I think I'll try to put this on a later homework assignment. Okay. Let me tell you now another lemma about connectedness and continuity. So let's take X connected and F, a continuous function from X to some other space Y. So then, and let's say it's surjective. So then Y is connected. So for example, we proved earlier that 0, 1 is connected. And so then we conclude that the circle is connected, since the exponential map gives a surjection from 0, 1 to the circle. Yes. Yeah, maybe that's the only example I want to say now. So let me just give you the proof of the lemma. So this is quick. So if Y is disconnected, I guess we'll prove the contrapositive. Suppose Y is disconnected, so then we can write Y as U union V of open, non-empty, disjoint sets. So then X, let's just take the preimage of these two, F inverse of U union F inverse of V. So these definitely cover X, and they're open sets because U and V are open, and they're disjoint. And so then this implies X is disconnected. Okay, so this is the contrapositive. And so if X is connected, then Y is connected. Great. Okay, so I think the last thing I want to do in this lecture is one more example, which is the topologist sine curve. So remember, this is defined. So we have the graph of sine 1 over x. And then we have the interval 0 times minus 1 to 1. So x, yes, so let me write this. So x is the union, this union. So the graph is x comma sine 1 over x for x positive. And the claim is that, so this is a topologist sine curve, and the claim is this is connected. So despite the fact that, well, I guess the way I've written it now, it has two pieces, but okay, neither of these pieces is, or these two pieces aren't both open. I guess this piece is open in X, since if you intersect with the open half plane here, then you get this set, which is then open in the subspace topology. But this set is not open. So let me give these names. So here's I1 and here's I2. So here's a sketch of an argument for why, for the claim. Let me try to get a little more space here. Yeah, so suppose X is U union V with U and V open. So I1 is connected. So I1 is topologically equivalent to the interval 0, 1 is connected. And so this means that I1 is either entirely contained in U or entirely contained in V. Because, well, the intersection of U and V with I1, it will give you open subsets of I1, and, well, I1 is disconnected, so is connected, so you can't write it, you can't disconnect it. Okay, and, sorry, this was supposed to be an I1 here. But the same is true for I2. I mean, I2 is topologically equivalent to the open interval here, which is connected. It's topologically equivalent to R. So it's also either in U or V. But here's the point. Any open set containing in R2 containing I1 contains points of I2. Right. So this means that if I1 is in U, then U also contains points of I2. And then since I2 is either entirely in U or entirely in V, that means I2 is, both I1 and I2 are either entirely in U or entirely in V. So from this we conclude U and V are not both non-empty. Okay, and so this, from this we conclude X is connected. So one final remark, which is that in practice, it can be hard to show a space is connected using only the definition. Directly from the definition. I mean, it's one of these things. I mean, to show a space is disconnected is easy because you just have to find U and V. But to show it's connected, you have to show there doesn't exist any U and V with these properties. So for example, well, you know, we'd like to show some of these spaces are connected, but this is a pain with the definition. So next time, we're going to discuss something called path connectedness, which is easier to show for a space, and we'll see that path connected implies connected. So this will be a way to show spaces are connected. And maybe just in a picture, path connectedness means that if you have 2 points in the space, then you can find a path between them. And well, all 3 of these examples have this property. Any 2 points are connected by some path. And we'll see next time that if you have this property, then the space is connected.